would first like to thank the organizers for the kind invitation. So, what I will give you first is think that you have a surface in three-dimensional space, and you should really think like of a sphere, and you should think that could be like a planet, an aqua planet, that is completely covered with water, and the water would be like, we think of it as being incompressible and having viscosity. So what you want to do is you want to have a model, a mathematical model that captures the situation, and then you want to make predictions what the fluid is going to do. So you will see, I will give you like a little bit like a detour of what kind of models have been proposed in the literature, and you will see they are all equivalent. So at the beginning, I will suggest a model that had been used like for people doing numerics of the situation, and which kind of avoids a little bit the language of differential geometry, but then I will also turn around and show you how things are formulated in pure terms like of differential geometry. So if you have a surface, then we have like different objects attached to a surface, so the tangent bundle. You could think of that you have a vector field on the surface, and this all depends that you have an ambient space.
Just a minute, it seems that the slides don't change.
Okay.
So stop share and share again. Sorry. I hope it works now.
Okay, I will start from the beginning. So then you have the terms like the orthogonal projection, and they have several terms that play a role, like what's a surface gradient, what's a surface divergence. So these are the objects that you will see first. These have to do with the geometry. Now the physical situation is that there is a fluid, again, occupying the surface, and being a fluid, it has a certain density, and it has a certain velocity. And if you want to say something about the physics, then it's a good first approach to say something about the stress tensor. So if you do that one way, and this would be like, I would call it a semi-intrinsic way of describing what the equations are. And you see various things, so you see this would be like more or less an intrinsic thing, but what comes out here, because I'm not yet using like covariant derivatives, you want to project it down. So you have, it looks similar to the well-known Navier-Stokes equations in Euclidean space, except for that you see all the projections which kind of projects it down to the tangent space. So this is a well-known formulation that you can think of, but you have to say something about what is the stress tensor here. And if you look at the stress tensor, then there is a well-known approach relying what is called the Boussinesq-Scriven approach, and usually you see that rather in the situation where you have bulk phases and then like a free boundary surface that separates the bulk phases, and it's a material surface. So if you go for it, then you can, that would be the proposal, you have like deformation tensor here, and then you would write down what is kind of also well known if you are in Euclidean space, except for that here you restrict yourself to the surface. So you see that in general you could apply it to vector space, to vector fields that are just in, so it's the surface is embedded in our N or R3 vector fields that not necessarily are tangential. You project it down, you do something, well, avoid writing down the definition, but you do this, and you get the stress tensor. So if you have it, then I will repeat what the equations are, and now it's explained at least what we mean physically by this. Now it comes as no surprise if you start with a tangential field, then the equations of course are written in such a way that you stay tangential. You can, if you want, you just take the derivative and show it. Now what's more interesting is, so here you have in this ones, so you have the viscosity somehow, so, and we have to say more about what's hidden in here. And we know if we were like in Euclidean space, then what would come up, obviously, or would be a Laplacian. But as soon as we are on surfaces, we have to be more careful. What do we mean by a Laplacian? And there are several proposals what a Laplacian should be. So one can compute it, and what comes out is, if you go through the computations with the given assumptions, then what comes out is something now that is purely actually intrinsic. So this is now and it should be intrinsic, because at the end you only want to see the surface and not the ambient space. And it's intrinsic in a way that you can also formulate it for any Riemannian manifold. So what you see here is there is a certain that looks like a Laplace operator, but I have to tell you more. But then there is a correction term that you wouldn't see in Euclidean space. In Euclidean space, this would just be 0. So it's the Ricci curvature that shows up here. So this is what comes out. This gives us like that dissipation, the dissipation term. Now I will tell you like what's the deal with the Laplacian here. And this one, if you write it in this way, this is the so-called Bochner Laplacian. Again, we have to be careful if you're on a manifold or on a surface. That's not the only candidate that you can apply, and I will give you like another candidate that usually shows up. And again, the Ricci curvature. So again, to repeat myself, so this is now purely intrinsic, and I could have started with this from the very beginning. So in two-dimensional case, it happens that if you look at the Ricci curvature and apply it, that's the same as just going for Gaussian curvature, which would be a scalar, and then you apply it to the tangent field, and now you have a vector field here. So this will be the equations that I will be looking at, and relying that I have like the insight what the dissipation here is. Now, if you want, you could have started from the very beginning and use like different terms in differential geometry, and then the way you would do it is what the usual transport term here is. This has to do like with the Levi-Civita connection. Here you look at if you want the covariant derivative, and that is a purely intrinsic formulation, and then you write it, so you can write it here. Now, there is an important connection between what we call the Bochner, or some people call it the connection Laplacian, or the rough Laplacian. There's a relationship between what's the Hodge Laplacian. And in the literature, that's many, well, not many, but in some papers, this had been used. So the Hodge Laplacian is something that by definition acts on one forms or on cotangent vectors, or not in vector field. So whenever you use it, you need the interpretation that you have a vector field, you convert it into a one form, you apply it here, and then once you're done with it, you have a one form or a covector field, and you go back. So this is the connection, and you can, if you want, you can go back and forth. Now, what I did here is I'm kind of just reformulating, and this is something that shows up in the literature, and if you go back and kind of replace it in, then the equations can be also formulated in this way, and then it's advantageous to write it as a gradient, not to confuse the nabla here with the connection. So let's look a little bit into this set of equations, because this has been also used in the literature. But before I do that, I should just say a little bit more about like the way I initially motivated it. So this has been really motivated by people that do numerics about it. We have like, this has been derived based on physical principles, hydrodynamic principles, and there is an alternative derivation by this group of mathematicians. And based on like the derivation, there is also numerical work, and I will show you some simulations by this group at the end. So starting with the way I did, also has a background. This has been motivated. Now I hope I have someone explain that if you want, you can switch it and look at the purely intrinsic formulation, where only like quantities in differential geometry show up. Now it's important to really stress that one should not neglect this Ricci term here, And that was first actually observed by Ebin and Marston in their famous paper, but it was rather added in a note at the very end that this should be the correct formulation. So this formulation has then also been looked at by Michael Taylor, and here you can see what has been done with it, and by Anna Mazzucato. And then the same formulation has been probed like manifolds in hyperbolic spaces. This is kind of a really interesting paper that discusses various proposals and what the drawbacks are. Since in particular they discuss why the Ricci curvature here should be included, otherwise things what you expect can go wrong. Now if you look at it, and there has been related work even earlier on, but at least in this related work, so the Hodge-Laplacian is used, but without including the Ricci term. And also our friend Edris Titi has worked with it. You can see, so they were interested in Gieri regularity, and that rather had a physical background, like deciding how many degrees of freedom can there be. And there's even been older work. So the equations have been looked at before, but not necessarily from a point of view like what is the dynamics of the equations. So I will now switch to like a mathematical analysis. So if you want, you can look at the equations again. And just for convenience, I will now use for the transport term this formulation. I will keep the surface gradient in this way. And you can ask what would happen if you look like local coordinates. So you go like to a point on the surface. I should really mention the surface do not have a boundary, and localize it and see what is it in three-dimensional space. If you want to localize, then what you see is this Bochner-Laplacian can be written in local coordinates in this way, where one just wants to be careful. These are like the covariant derivatives, so there is a change. These are not the usual partial derivatives, the covariant derivatives. It looks formally, it looks like a Laplace-Beltrami, but it's different because of covariant derivatives. And if you look at the Ricci, so it's usually the Ricci tensor is a 2-0 tensor. So what you do here is you convert it into a 1-1. Then you apply to it, and out comes a vector field again. So if you want, you can take that, and that's what we did, and localize it. And if you localize it, so you have partitions on the manifold, you have charts, you go down, so you can have like n copies of localizations, and you look at that in RD, so what you end up are not the usual, like it doesn't look like the usual Laplacian. There are correction terms that come from the geometry. But you can do that and study things in three-dimensional or in three-dimensional space or d-dimensional space and do your best to solve it, and then you transport it back and patch it together, and then you will have results on the surface. So one result that comes in that we proved, and this is still work with Jan Pruis and then Matthias Wilke, he's also here. So you can look at the usual, what you would usually do. You can look at the Stokes operator. So you want to establish that there is a Helmholtz projection on, so these are compact surfaces on compact surfaces. Now it's a convenient fact here that this has maximal regularity. In fact, if this would be like the ending up equations would be semi-linear, but it's convenient to look at it from a point of view of maximal regularity. If you do that, then you can establish local existence. And this is not a sharp result, but it gives you like one way that you could study it. And I will just say, like, didn't want to be too technical. We have a way to build in time weights, and you can drastically decrease the initial regularity. So it has solutions. Solutions we can also show. Solutions regularize. Solutions would be analytic in time, and that would be like C infinity if the manifold is C infinity. So this gives you a way. So now you have uniqueness of solutions, and you can start thinking about what are solutions really doing, and then it becomes interesting. What is the asymptotics here? So before I do that, I will say you can even do better and look at the Stokes operator and show that it has an H-infinity calculus. What is the advantage if you have H-infinity calculus? What you can do is you can think about what we call critical spaces. And here we should be a little bit more careful. So critical spaces, we saw that before in Senjo's talk. If you are in Rn or Rd and you have scaling invariances, then you know what you mean by critical spaces. However, you can also define them differently, and that has to do with time weights. And you decide what is like the maximum, the critical time weight, where you still have well-posedness. And we can do that, and it turns out, like with this idea of critical spaces, if you go back and you are in a situation where you have scaling invariance, then these are the same spaces. So it means in that sense, what we have here, in our sense, critical spaces, it's more general, more flexible. Now, if you do this, so as soon as you have the H-infinity calculus, you can do critical spaces, and you end up seeing like the typical spaces that look similar to what Senjo had, except for that we are in a different range for Q and P. Q and P should be strictly between 1 and infinity. But what you see here is, so you could decide to make Q bigger and bigger and bigger, and you see, and you should look at this framework here, and that means you get closer and closer to -1. But of course, you cannot just take Q to be infinity and P to be infinity. It wouldn't work, and anyway, it wouldn't be well posed. Now, if you look at it, so I'm saying a strong setting, a weak setting. So weak, you should not read in terms of like weak solutions, Le-Ray-Hop weak solutions. It's rather, where you look at the equation, strong would mean that you take a base space that is an LQ space. Weak would be that you take a ground space that is an H-1, and then you can formulate, you can transport and look, so you give meaning to the equation. So you see here, it's kind of really amazing. Whatever you do with P and Q, the Sobolev index doesn't change. Now, what does it mean, like in some situations, if you are on a two-dimensional surface or three-dimensional surfaces, and you would rather want to look at the case where you choose P and Q to be 2 simultaneously, and you see here in this weak setting, you are allowed to take P to be 2, then you get a 1 here. And if you are two-dimensional surface, you have a 2 here, you take Q to be 2, and you can match this inequality here. Let's see what comes out. So if you are on a three-dimensional surface and you choose P and Q to be simultaneously 2, then you end up, you can start with initial data in this space, and this is kind of well known in the Euclidean context of Kato spaces. If you are in 2 dimensions, then again you can look at this, and then you're allowed to choose initial data. In this case, that are all L2 initial data, and you want them to be divergence free. So what I'm telling you without really stating a theorem here is we can solve, if you have a 2-dimensional surface, we have solutions and uniqueness. So we have existence and uniqueness for initial data in L2 of solutions, and the solutions would immediately regularize, so they immediately become strong and regularize even more. So I will return in the second half of the talk, or the last third, and look specifically at the situation that you have 2-dimensional compact surfaces, and then you can really say a lot about what solutions are doing, and you can exactly say how they behave. Before I do that, I would like to go back and look a little bit more about dynamical properties of the model here. You can, in the usual way, you define an energy, a kinetic energy, and if you take the derivative, then you end up having, also that would also be well known in a Euclidean setting. We have here the deformation tensor. So it is interesting to know, does the model have equilibria? And if you have equilibria, then of course that the energy is constant, then you take the derivative. So this would be a 0 here. So this forces this term here to be 0. So if you were in Euclidean space, then you would be saying that means that the U is rigid motion, which means if you're free in R3, would mean you have translations and rotations. So on surfaces, you don't have like this type of rigid motions. You could still call this like the rigid motions on a surface. Then it's interesting to know like what surfaces or do surfaces have rigid motions here. Before I do that, I will kind of just go back and say, well, once you decide at equilibrium that you have that the du here vanishes, then you can go back and say, if this is gone, then you can actually convince yourself that there is a relationship between the pressure here and then, well, the gradient of the pressure and the gradient of the square of the velocity. So this means you end up with equilibria, and the unknown here is what is really contained in here. And on a side, for those of you who are past, this condition, in fact, is redundant if the deformation tensor vanishes, and if you take the trace of the deformation tensor, then you would have the divergence here. So this one I could take out, it's automatically satisfied. So now we have, so this would characterize the equilibria, and then the big question is that kind of an interesting situation? What are the equilibria? Now it turns out that people in Riemannian geometry have been dealing with this situation where the deformation tensor vanishes, and there is a characterization or a name for those tangential fields which satisfies it. And the name is, you can look at Killing field, and you should really pay attention. Killing is capitalized, so it's a name and not something else. So it's not that these fields do something bad to the geometry. So you have this, and then you go back and decide, well, in case that the deformation tensor vanishes, which means in the case that we are at an equilibrium, that means we are dealing with a killing field on a surface. So that means now you can go back and see what do people in differential geometry know about killing fields. And so this is kind of, well, that's what then, but more interesting maybe is the second one. If you want to really think about killing fields and now away from hydrodynamics, then you should know if you have a vector field and you hope that it's a killing field, then you could look at the flow that the vector field generates, and in case that you have an isometry, then you're looking at a killing vector field. So this is kind of a useful knowledge here, because especially if you are in two-dimensional manifolds, and then you know if you're looking at the vector field, and again you hope it to be a killing field, then you go back and say, well, then you're dealing with isometries, and isometries according to like the Gauss theorem, egregium conserves the Gaussian curvature, so you can only have, so this kind of restrict what kind of killing fields you would have. And then it's something, so you can characterize like situations where the killing fields are trivial. So I should mention trivial, so being a subalgebra, in particular killing fields form a vector space, so 0 is always a killing field. The question is, are there more than 0 vector field? This is kind of interesting. You have an estimate, or you know what the dimension is, so the dimension can be no larger than what's written here. And then you look at and say, well, if you take, let's say, a sphere, if you have a sphere in three-dimensional space, then D would be 2, and you look at it, and then you know that the dimension would be exactly three-dimensional. So you go back and ask, so now that we know that a sphere supports killing fields or equilibria, then you can think what could they be. So it has to be something of 3 dimensions. You can think like what would a vector field be that generates isometries. And if you look at it, then what comes out is on a sphere. You can look at, so let's maybe just for the sake of definiteness Let's look at rotations around the z-axis. And that would be one possibility to realize a killing field. But then we know we can look at any axis, and if you look at any axis, then you can just see how many degrees of freedom do you have to give an action, to describe an axis, and that would be 3 degrees of freedom. So here we are. That means that if we were now looking at a flow on a perfect sphere, then it would have equilibrium. And the equilibrium would be, you would have a fluid, let's say if you look at this, that would simply rotate around, and around. You can also look at the different things, so you can look at the torus here, and then you decide in that case, and also, it also supports a killing vector field or equilibrium. This would again be the rotations. So good, this tells us that there is an interesting situation with killing vector fields. And now what you can say, now you can go back to the equation and say, well, what can you say about the dynamics? And it turns out that we can prove if you start close to an equilibrium, to a killing vector field, then in any dimension you have global existence. And what the solution will do is the solution will, so global existence, and the solution will converge, but not necessarily so you can say you start in a neighborhood of this equilibrium. It will converge to an equilibrium, but it might not be like the one that where you started out close to. But you can say more. It's actually, so this stands for the orthogonal projection down onto the vector space, the finite dimensional vector space of killing field. You can prove that. You just have to be careful that it means in the case of killing vector field, it has some symmetries. That means if you look at and want to apply like linearized stability, you have to be careful that in that case 0 will be an eigenvalue. It will support eigenfunctions, and the kernel will have, so you can show that the kernel will exactly have the dimension of the killing fields. So there is a correspondence between the equation or the dimension of the kernel and then also like the dimension of the killing field. And you have to do a little bit more, but there is something that we know very well how to apply it, and then you have, then you show global existence and convergence. So this is not unexpected. It will relax to an equilibrium if you start out. Now comes the situation that, so now let's be more specific and look at the two-dimensional, again, compact manifold without boundary. What can you say? And we know, like, if you are in Euclidean space, 2 dimensions, then we know things usually are good, so you can expect global existence. Is the same true here? And the answer is yes. So you can start with your favorite initial velocity that is in L2, and it's divergence-free. Then I'll guarantee you that the solution exists globally, and it will converge to an equilibrium. So that means no matter how you start, it will always relax to an equilibrium. So if you were on the sphere, it means if you start out, then it will relax to an equilibrium. And it depends then very much on, if you start out, it depends very much whether or not the projection to the killing fields of U0 is. So whether you, well, what the projection is. Now, so this is kind of the best result you can hope for. And you see I'm kind of giving you even the convergence can be in a very good space. So for definitely we chose this space. But due to parabolic regularization, it would also converge in higher norms or topologies. So it's a very good convergence. In particular, you certainly have pointwise convergence. So if you do that, so what is involved? Well, the critical spaces, the critical weights, and we have something that we call extrapolation scale. And then you want to be careful that in the case of, so an energy estimate will be involved. That means you will have to deal with Corn's inequality, but then you have to be careful that Corn's inequality only holds if you are perpendicular to, or you factor out the killing fields. Then you have parabolic regularization, and you can show that. And at the end, I will have some numerical simulations. And courtesy, you can see who produced it. But before I show you this, let me just give you just a little bit of hint where these things come from. So you can look at this subspace here, like the script E, and we know, so this means Killing vector fields. It's a linear subspace and it has finite dimension. And you can look at, so what you can do is you can look at the complement, and the complement you want to say like with respect to the L2 inner product, and then you show that you have a direct decomposition here. So it's interesting in this case, if you start with an initial value that is perpendicular on the topologic or on the complement of the killing fields, then you prove that you stay so. So if you start perpendicular, you stay so. And based on that and Korn's inequality, you kind of derive an energy estimate. And this means here you see that you can replace. So originally, if you do the energy estimate, you would have the deformation tensor or the symmetric gradient. But here you see that with Korn, you can replace it by the H12, and then you have an energy estimate. And at that moment with the energy estimate, then we can go back and show global existence. And you can show a little bit more. This comes out from the same principles. And so you see in an L2 topology, you have exponential decay. And then you can do better by going back and doing like bootstrapping and parabolic regularization. And maybe I'll just show you. So at the beginning, it's like a cartoon, how you start with an initial value, you can decompose it, something that is perpendicular, something that is in equilibrium, and you solve it. You have to be a little bit careful that here it seems you are just adding solutions, but this is a nonlinear equation, so you have to kind of linearize the equation and still show that things go right. Now we'll go back and show you simulations here. Maybe I will start with that one, and probably I have to go back and click on it. So you will see a sphere. It works. And let me go back here and start. I will try to stop it here. Stop. And you see that at the beginning, you see that there are things going around in various directions. So the theory tells you that this thing wants to relax to a killing field or to like a steady motion. And you can kind of guess what does it want to do. Well, the numerics will tell you. So we'll go back and we'll relax and relax. And at the end, you kind of really see the motion around. You see on top, there's still some adjustment. But at the end, you see, so this is a killing field, or it relaxes to an equilibrium. Now let's see if I can go back here, and I might need help from an expert to...
AutoHero, c'est le site pour acheter de voitures d'occasion en ligne.
That was unintended, yeah. Let me see, how do I go back here? Like just this guy here, or maybe not? Yeah?
You want to go back
to the slide? Yeah. Okay. We should just find the PDF file.
right.
Yeah, and yeah. Now I will show you something else that shows more drastically what can happen on a sphere. And that will require a little bit some thinking, what is really going on here. Let me go back, start here. And you see that they started out with something which has a vertex. And numerically, the people again around, so I should, again, Maxim Olchanski, and then people in Germany, in Aachen, and in Houston. So I'll just let it run for you. You see, it's really interesting, but then we have to understand how does it comply with the theory here. Did it stop? Or I didn't even start? No, it still does. So the vertex kind of persists. You see it by the colors that the velocity or the speed is decreasing. Still persists, But speed is decreasing like in both directions. And now you're asking, so I kind of promised you we can guarantee what the solutions are doing. And here it seems that they're not really doing what I told you they should be doing. And what's the trick here? So at the end, what you see is, so this is a case where you started out and the projection or what it does here is it will converge. The theorem is correct, at least we still believe so. And so this wasn't intended, so that's not. So what happens is it will converge to a killing field, and the killing field is simply the zero field. What means, like, if I would follow it long enough, this thing would just die out and come to a standstill. And I have more than used up my time, so thank you very much for your attention.
Okay, so thank you very much for your very interesting talk. So I'm opening discussion. Are there some questions, remarks? Yeah.
Just one quick question about the model. So you had two different types of viscosity, and one of them was this surface dilatational viscosity. What is the intuition behind it? What is the meaning of this viscosity?
So at the end, it had two viscosity, but it would only show up in case that the divergence is not zero. So as soon as you have divergence zero, one goes away.
Okay. So it's like in the compressible situation where you have bulk and shear viscosity.
Yeah. Yes.
Oh,
yeah.
okay.
Yeah. You can take that as a
Thank you.
compressible case. Yeah.
Okay.
So the question is, so if you look at initial data, and here I'm thinking about the sphere case, the 2D sphere, okay? If you look at any initial data, you can project it into the killing field space.
Yeah.
Okay. Is that projection conserved?
Yeah.
But not in general, right? If we've not talked about specifically about the 2D sphere.
It's if you start outside, then you can project down and look at what. So one would be an equilibrium. Nothing happens. The other projection would just be you know that it stays outside. And it's interesting, it's preserved for, if I write down the equation as a nonlinear equation, or I can linearize it on an equilibrium, then it becomes linear, you have like additional terms, and also preserved in that case.
Okay, thanks.
Okay, so other questions?
It is possible to consider a Prandtl type system in the sphere case, for example, with epsilon neighborhood.
Say that again. So in the case that
in the case of a sphere with
sphere,
with epsilon tubular neighborhood, it is possible to, with this model to adapt this.
so you have the sphere, and you want to consider a
in the stripe around the
so
sphere.
you want to have a tubular neighborhood of it.
Yes.
Yeah. So this would be like a different situation, because here you just think of having just a surface and having fluid like sitting on the surface and never moving away.
Yes.
So if you have a tubular neighborhood, you would have some fluid to consider some fluid outside, and then it doesn't really do justice to the situation.
Okay, thank you.
And by the way, you might argue that the Earth is not fully covered by fluid, so that means like it wouldn't cover the situation of the Earth. But then what we are working on is you can also have like you can look at the Earth and then put in oceans or land mass. That means you have a situation with boundary conditions, and we think we can prove like boundary condition means what kind of boundary conditions. For instance, slip or partial slip, like where the ocean meets the land mass, and we think we believe we can prove a similar result in that context.
Okay, thank you.
Thank you. Thank you very much for a very beautiful talk. And I have a curious question, very curious. So normally on the Riemannian manifold, we have the non-uniqueness of Navier-Stokes solution to Navier-Stokes equation, because now the Helmholtz-Leray projection has to be understood as Kodaira-Hawk projection, yeah? And it contains a non-trivial harmonic one form.
I think that would happen if your
Well,
Riemann surface is not compact, then you're in danger. But
and here you have a non-compact surface, and then you can get rid of that.
That would, if you're non-compact, then you have to be careful with.
Yeah, and the question is,
Yeah, you go on.
Can you extend that to the case, for example, only locally compact, or like hyperbolic surface or something like this?
I think we can do that. If you if you have non-compact surfaces, you kind of have to bring in something like some geometric restrictions. And one thing that we think we at least are willing to believe that we can do is something like called uniformly regular manifolds. That's something that Amann has done a lot. But then I agree, when the non-uniqueness of the decomposition, something that one carefully has to study. Yeah.
Okay, so are there some other questions or remarks? So it seems to be not the case. So thank you very much again. Thank you very much.